Hi, my name is Michael Pinter. I'm currently a PhD student at the University of Oxford, and I'm part of the Goals Group in the Oxford Robotics Institute. Today I'm going to present our work on convex hull Monte-Carlo tree search for ICAPS 2020. In this work, we're interested in problem situations where we have multiple conflicting objectives. For example, we might have a robot that needs to complete tasks in some environment, but it needs to minimize battery usage, but it can't go and complete the tasks without expending some of its battery. To reason about our multi-objective problems, we consider multi-objective Markov decision processes. This is similar to a single-objective Markov decision process, containing a state space, action space, reward function, transition function, a finite horizon, and an initial state. However, now, the reward function returns a vector value. For single-objective MGPs, we typically try to maximize the expected return. Because there is no single optimal policy, we instead compute a set of best policies. We call this set the convex hull. The Pareto front is based on a partial relation called Pareto domination. One vector Pareto dominates another vector if it is greater in all dimensions and strictly greater in at least one of the dimensions. The Pareto front is then the set of undominated points. Or alternatively, the set of points for which to improve in one objective you'd have to compromise in at least one other objective. To apply this in the case of multi-objective MDPs, the set of points we consider corresponds to the multi-objective values of different policies. In the figure, we can see a set of points, and the convex hull is highlighted by the blue points. Now we will consider the convex hull value iteration algorithm. Convex hull value iteration is an extension of value iteration for multi-objective MGPs. Firstly, an arithmetic over sets of vectors needs to be defined. This allows us to add two sets of vectors, multiply by a scalar, and add a single vector to a set of vectors. By using this arithmetic, the Bellman update equations can be adapted for the multi-objective setting. These are largely the same, except the max operation is replaced by a prune operation. However, convex hull value iteration doesn't scale well for larger environments. In single-objective settings, one approach to tackling this scalability issue is to use a tree search. So next we will consider trial-based heuristic tree search, which later will allow us to add elements of convex hull value iteration into a tree search for a multi-objective planner. The prune operation, given a set of points, removes all points except those on the convex hull. Trial-based heuristic tree search is an algorithm schema that generalizes Monte-Carlo tree search. There are four main parts of trial-based heuristic tree search that we will consider: action selection, outcome selection, the heuristic function, and the backup functions. In trial-based heuristic tree search, we build a search tree by considering successive trials in the MDP. For each trial, we traverse the tree alternating between action selection at decision nodes and outcome selection at chance nodes. Decision nodes correspond to states, and chance nodes correspond to state action pairs. Anytime a new node is created, its value is initialized using a heuristic function. Once a leaf node is reached, the backup functions are used to update all the nodes visited on the trial inductively. In single-objective problems, often the upper confidence bound method is used for action selection. Outcome selection typically consists of just sampling from the next state distribution, and the heuristic function is used to give an initial value for each node when it's created. Some algorithms following the schema will just ignore the heuristic function and set the initial estimates of each node to 0. However, one example of how the heuristic function can be used is to incorporate a Monte-Carlo tree search style rollout estimate. Finally, the backup functions are used to update the values stored in each node. As an example for single-objective problems, these backup functions could be the Bellman backup functions, but they could also just compute a sample average. To arrive at convex hull Monte-Carlo tree search, we use the convex hull value iteration backup functions as the backup functions in our trial-based heuristic tree search. We should note to perform these backups, the standard scalar value estimate needs to be replaced for a Pareto front value estimate. In our paper, we discuss in detail about action selection. For this presentation, I will give a brief overview of what we discuss in the paper. One way that we can analyze the performance of our tree search in a multi-objective setting is to pair each trial with a context, which is a weighting over different objectives. And by considering these contexts paired with each trial, we can then consider contextual regret. As the problem of action selection at decision nodes can be considered a non-stationary multi-armed bandit problem, by associating contexts with each trial, that non-stationary multi-armed bandit problem now becomes a contextual non-stationary multi-armed bandit problem. And therefore, for similar reasons that the upper confidence bound method is used for action selection, we use the contextual zooming method for contextual multi-armed bandit problems to select actions. And therefore, for the same reasons the upper confidence bound is commonly used in single objective problems, we decided to use contextual zooming for our action selection. Finally, in our paper, we show that action selection needs to take into account contexts if it hopes to achieve a sublinear contextual regret. For our experiments, we use the generalized deep-sea treasure environment. On each trial, there is a submarine that starts in the top left corner. On each step, it can move in one of the cardinal directions. If it tries to move out of the environment, then it doesn't move at all. For each step, there is a time cost of 1. The time cost is the first reward, and the second reward is treasure collected. In the visualizations on the slides, the treasure is represented by the squares with numbers on them. Treasure is more valuable the deeper it is found, and the trial ends when a single piece of treasure has been collected. The generalized version of deep-sea treasure has a variable number of columns that can be used to vary the scale of the environment. It also has a transition noise, a probability that a strong current sweeps the submarine into one of the adjacent squares. We use GDST of CP to refer to a problem with C columns and a transition noise of P. To assess how good a convex hull is, it is common to use the hypervolume. The hypervolume considers an n-dimensional volume between a reference point and a convex hull. For example, in 2 dimensions, we can think of it as the area under the convex hull relative to the reference point. It is generally considered a good measure of the quality of a convex hull, but cannot be used to draw direct comparisons between convex hulls. Analyze the scalability of convex hull Monte-Carlo tree search. We compare the performance of each algorithm when limited to a budget of 25,000 backups on a range of environment sizes. To normalize the results, we plot the ratio between the hypervolume of the optimal Pareto front computed by the algorithm given its computational budget. Next, we considered multiple action selection methods, including those from prior multi-objective Monte-Carlo tree search works. On a low computational budget, convex hull Monte-Carlo tree search outperforms convex hull value iteration, but convex hull value iteration will compute the optimal Pareto front faster. These trade-offs are well known with Monte-Carlo tree search methods. We see that the contextual zooming action selection outperforms the action selection methods from prior work, achieving a higher hypervolume with respect to the number of backups. Thank you for taking the time to listen to this talk, and please contact me at my email if you have any questions.